All right. Anybody have any questions about the assignment or anything from last time? Okay. So we're done with all the vectors stuff. Now we're going to get into statics. So we're going to start with particles. Almost everything we do in this class is going to be rigid bodies. But we're going to start with particles, which is most of what you did in Physics 1. So particle statics. What is a particle, first of all? I think it's sort of natural for people to think a particle is like a small thing because you think of particle physics as like subatomic particles and stuff. But really a particle is just a mathematical treatment and you can use it for anything. A particle is a mathematical treatment of an object as having no length dimensions and as a result of that, and therefore no orientation. Okay, so you can't, if nothing has a length dimension, you can't tell which part is its head and which part is its feet and stuff like that. There's no orientation. It's just an object in space. It does have mass. Position, velocity, acceleration, but it just doesn't have orientation. Okay, well, if something doesn't have an orientation, it doesn't have length dimensions, you can't make any distinctions about where forces are acting on the body, And so you can't make anything spin. Like think about talking about moments, and you probably saw a picture of a wrench or something when you first talked about moments or torques, And the way you make the wrench turn is you have one force acting where the bolt is, a reaction force with the bolt. And then you have another force that's like the hand that's changing the orientation. There's nothing like that if you don't have length dimensions. So you can't have any moments. Also, I'm going to always use the word moments in physics. I think physicists generally think of moments and torques as the same thing. In engineering, when we talk about a torque, we're talking about a very specific kind of a couple, really, like torques going in opposite directions at a distance from each other that are twisting an object. So I'm going to use the word moment for what your physics professor might have called torques, And so the only governing equation is Newton's second law. I'm going to write this so many times, I'm going to just abbreviate it N2L, Newton's second law. And so Newton's second law says F net is equal to the mass times the acceleration of the center of mass. Since we're talking about statics and everything in this class is going to be in is going to be in equilibrium. There's not going to be any acceleration of the center of mass, and so our governing equation is just going to be the net force factor is equal to 0. Okay, so that's particle statics. And everything is just derivable from that. But any time that you use Newton's second law, or the moment equation that we'll get to when we get to rigid bodies, so whenever you use Newton's second law, or the moment equation that isn't going to be useful here, you need to draw a free body diagram. I'm going to abbreviate that FBD. But it's just a way to, so Newton's second law, F net is equal to mass times acceleration. The free body diagram is just meant to show you all of the forces acting on the body. So once you draw your free body diagram, you put each of the forces in your diagram onto the left side of Newton's second law. And then, in general, you only have the right side to deal with. In statics, really, you're done because we're not going to ever have anything on the right side. So the free body diagram is everything, you know. Okay, so here's what I want to see in free body diagrams. Probably, in most physics classes, like you probably are used to drawing your free body diagrams as like a dot with forces coming out in different directions. That's because in physics, you almost didn't do anything except particles, like almost the whole class is particles. In statics, almost the whole class is going to be rigid bodies. So instead of starting with a point, I want you to start with an outline, a rough outline of the thing that you're isolating. Okay, so here are the steps for a free body diagram. First, draw a closed outline of the body. And this drawing, let me add this little thing in parentheses, or the part of the body or the collection of bodies that you're isolating. In this outline, there are no internal details. And no external objects. The whole point of the free body diagram is to be very clear to yourself about where the boundary is between what you're isolating and what you're not isolating. Okay? Okay, second, draw all loads. And by loads, with particles, you're only talking about forces. Later on, when we talk about rigid bodies, this will also include couples. Did the word couples come up ever in physics? Maybe not. Okay, but we'll talk about that pretty soon. Couples are pairs of forces that in equal and opposite directions, and you can just treat them as pure moments that you add onto the thing. You don't have to treat them as forces. So we'll get to that, though. So draw all the loads applied to the chosen body by the surroundings. You can think of these mentally as being divided up into two categories. I'm not going to write this down, but there are only two kinds of forces that there can be. Field forces, which are almost always in this class just gravity, but it also could, bless you, it also could include magnetic field forces, electric field forces. When, like in Super Friends and stuff, they talk about force fields, and force fields are like really cool, but in real life, force fields are, like gravity is a force field. That's not really that cool. We're pretty used to it, But what a field means, it means the same thing as a conservative force. It means that if you're given a location, that's enough information to determine what the force is that's applied to the object. Okay, so gravity is a really boring one as long as we're close to the surface of the Earth. It's just like the person starts to give you the location and you interrupt them and just say, it's mg down, bro. Like, I don't need any more. If you get farther from the surface of the Earth, it turns out that force field is really the gravitational constant times the two masses divided by the distance squared. But that's what a field force is. Okay. The only other type of force besides field forces are contact forces. And so all you have to do mentally to make sure that you've covered every force that's acting on a body is think, have I put the weight force in? Are there any other field forces? Probably not. And then go around the boundary mentally and say, like, there's contact, 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 contact. And so I have to deal with those. And once you've dealt with those four contacts, then you're done with your free body diagram. Okay. Okay, so if the direction of a force is known, or the direction of a load, then draw an arrow in the direction of that load. When we get to couples later on, forces will just be a regular arrow like that. Couples will have a double head like that, which I guess are just meant to show that it's the two forces of the couple. But either way, you're just drawing an arrow in the direction of the load. And then label that arrow with a scalar, value, or variable. Okay. Once you've drawn that arrow, all you need to define it is just the magnitude of that vector. So all you need is a scalar at that point, a number. Okay. Second, if the direction of the load is not known, Draw an arrow in each axis direction. So force would be like this, or a lot of times you see people do it like this. It doesn't matter which one you do, but that would be for a force. If it's in 3D, you have to show all three. And a couple would be like you would imagine, just these components, these axis directions have double heads. And this you have to label with a vector value or variable. Bless you. Okay. So we're going to have problems where, things get fairly complicated. And let me just go through sort of a complicated case and how to sort of approach this. So let's say you have a pickup truck. That's not a very good pickup truck, but it's really more of a flatbed truck, I guess. And it's sinking into the mud. Okay. And there's a guy standing on the hood. And there's a bird in the back, like a big, like one of those ones from Up,
Like an ostrich?
Yeah, like an ostrich, like a big, yeah.
This person's really got themselves in a predicament.
Yeah, exactly. He's got a lot of explaining to do. And then they're trying to pull this out using a rope that's attached to a helicopter.
It's a really rare species of bird.
In the movie it is.
Oh, yeah.
Okay, so let's say that's what's going on, and you want to draw a free body diagram of the truck. Okay, this is sort of like an example. So the idea is there's just a lot going on, there's a lot of stuff going on, but you need to be systematic about just thinking like, don't get carried away by like looking at the thing and saying like, this problem's crazy, just start going through the steps. So your free body diagram would be like this. Okay, so you don't have to be like an artiste, but we're isolating the truck. And so the person, the rope, the helicopter, the bird, the mud, you don't draw those. You just draw the outline of what you're isolating. Now, first, our field forces. There's no reason to think there's any significant magnetic or electrical forces going on here. Hopefully not. So the only field force is at the center of mass of the truck. There's a weight force. Okay. There's a force applied by the mud. We don't know the direction of that force, so I'm going to say that the center where that force is applied is down there somewhere, and I'm going to call that F mud. Okay. So like what I'm doing now that I've drawn the weight force is I'm just going around the entire, in this case, sort of three-dimensional body, imagining where the surroundings make any contact with the outline, okay? The mud makes contact, so I drew that force. The bird makes contact. This one, we know the direction is just going to be straight down. We don't know what the magnitude is, but I'll just call this F bird. Notice that my F mud variable is a vector because we don't know the direction, okay? The bird, that force is acting straight down, and so that's a scalar variable, okay? Same with the force from the man. I could have given these different letter names, but the subscripts make them different variables. And then if you keep going around the outline, the last place that the surroundings make contact with the outline is here. That's a cable force. I'll call that T. Okay. And so now what we have is, since we're doing this as a two-dimensional problem, how many variables do we have that we would have to solve for? Well, in 2D, we have two variables for the mud. We probably know the mass, so this isn't a variable. So 2, 3, 4, 5 variables. We could then isolate the bird and the man and figure out the force from the bird and the force from the man and whatever. But now that we've dealt with every place on the boundary that the surroundings make contact, we know we're done. There's no like worrying, like I hope I got everything, you know. If you deal with every place that the surroundings make contact with the boundary, that's all, okay? So it's just sort of a nice systematic approach. And now you know that these are the forces that go into the left side of Newton's second law. Okay, I have a question for you. In the wording of Newton's second law, it doesn't say anything about like all the forces acting on the boundary of the body. Why have I, so we did the field forces, and then after that, we were only concerned with forces acting on the boundary, okay? So why does the boundary matter so much? The wording of Newton's second law just says every force acting on it, right? I mean, there's forces going on inside that boundary, right? I mean, what if the engine's on, like there are forces inside the engine? Yeah.
Does it have to do with the action-reaction?
That's exactly why. That's right. So every force acting on this body that's inside that boundary is acting as an action-reaction pair, okay? So if the engine's on, the piston's moving, it's applying forces to the cylinder, but the cylinder is applying equal and opposite forces at the same point to the piston, you know? And so those cancel out, you know? And so that's why the boundary is such a like important thing in free body diagrams. That's why the only job of the free body diagram really is to make it clear to yourself about the boundary between the in crowd and the out crowd, you know what I mean? So that's why you want to draw a closed boundary with no gaps in it. There's no gray area about like, I don't know, like, are we including this little piece of mud here? Like, no, this is our boundary, the truck, you know? Okay, that's why. Action-reaction pairs, yes. Okay, well, anybody have any questions? All right, so I broke it up into loads where we know the directions and loads where we don't know the directions. So let's talk about some of the loads where we always know the directions. You know, I think you've seen these before, the ones I'm going to talk about today. One of them we're going to treat a little bit differently than you did in physics. Okay, so contact forces And contact forces, in this class, we're going to sort of treat in general as the group joints. Okay, this is what we're going to call a joint, a connection between two bodies. So contact forces or joints for particle statics. When we get into rigid bodies, that's when the more complicated joints are going to come up. But the ones that we're going to deal with here are cable forces. Second, frictionless contact between bodies. And third, friction contact between bodies. That's the one we're going to do a little differently than in physics. Okay, so the first one is cable forces. A cable always applies a force to the body. That's parallel to the cable, away from the body. Okay, so for example, if you have a pulley attached to the ceiling and a cable going over the pulley, connecting body 1 to body 2. Then a free body diagram of body 1. The weight force acts down, so I'll write that as M1G. And the cable force acts parallel to the cable, away from the body. So like that. And for body 2, weight force acts down, so I'll call that M2G. The cable force is parallel to the cable, away from the body, so it's up here too. And then, if it's the same cable, and it goes over nothing, goes through nothing except pulleys, then this force is the same as the other force. Every cable force applied by the same cable is the same as long as it goes over pulleys. Okay. Or, I mean, nothing or pulleys, as long as pulleys are the only thing it contacts with in between. Okay. Any questions about that? You've done all this stuff before. Okay, next is frictionless contact. So if two objects push against each other, so push on each other without friction, The force is perpendicular to the surface of contact. And toward the chosen body. So the pulling force is away from the body, pushing force is toward the body. So for example, if you have an incline and two carts on this incline that are pushing on each other, let's say this one's 5 kilograms, this one's 7 kilograms, and then you have a 100 Newton force pushing there on the 7. There are friction contacts between the incline and the wheels for each of these, and there's a frictionless contact between the two carts. Okay, so a free body diagram of the 5 kilogram there's a weight force of 5 times 9.81, so 49.05 newtons down. And now we look for the contact. There's contact between the ground and the wheels. Remember, with particles, everything happens at the same spot, so I'm going to lump it all into all of that pushing force from the ground to the wheels. I'm going to call it the same force. But notice it's perpendicular to the ground toward the chosen body. So I'll call that N5. Then there's a pushing contact on the 5 from the 7. So that's perpendicular to the surface of contact toward the chosen body. I'll call that R. That 100 isn't acting on the 5. It's not acting on the boundary of 5, so that stays out of there. Now the free body diagram for the 7. There's a weight force of 7 times 9.81. I think that's 68.67 if I remember. Newtons. There's a pushing force from the incline. So that's perpendicular to the surface toward the chosen body. Call that N7. There's a pushing force from the 5 toward the chosen body, perpendicular to the surface. That's an action-reaction pair, so that's R, just like the other one was. And then there's the 100 that's just given. We're not told what's applying that force. It's just given. Could we solve this using Newton's second law for these variables? Well, this is a 2D problem. So how many equations are we going to get? We'd have Newton's second law for the 5. That's x and y components, so that's 2 equations. Newton's second law for the 7 is 2 more equations. So we have 4 equations. So the most variables we can deal with is 4. So let's look and see what we have. 1, 2, 3. So we should be able to do that. Okay?
Question.
Yeah.
Normally, whenever I should free body diagrams the normal force, I just put it coming from the middle, would that be wrong?
Yeah, that's fine. You can put it wherever you want while we're doing particles. When we get to rigid bodies, where you put it is going to matter, because so like if we were doing this as a rigid body problem, and we will, eventually, you would have to have a separate normal force for one wheel and a separate normal for the other, because the way those normals are distributed determines the moment on the thing. But for now, put them anywhere, yeah. Any other questions? Okay, friction contact. This is going to be great. This is the place where things are easier than physics. We're not going to deal with coefficients of friction and stuff because this is static friction. And remember, static friction, the coefficient doesn't let you calculate the friction force unless you happen to be exactly at the maximum friction force. So it doesn't do us much good, So, okay, friction contact. So when you have a friction force in this class, it's just a force vector with an unknown direction. So for example, let's say you have an incline and two boxes sitting on top of each other. Let's say this is 1 kilogram and 2 kilograms. And let's say you have a 5 Newton force that's horizontal and a 10 Newton force that's parallel to the surface. And let's say we're going to use so in physics 1, problems like this, you always chose a rotated coordinate system so that it was easy to represent the coefficient times the normal for one of the components and the normal for the other component. Remember doing all that? And then you'd use sine and cosine for everything. In this class, there's no reason to use the rotated coordinate system. We're just going to use that standard coordinate system there, okay? And the way these free body diagrams will look. So free body diagram for the 1 kilogram. We have the weight force of 1 times 9.81, so 9.81 newtons. We have this horizontal 5 Newton force. And then the normal and the friction force is just lumped into a single thing. That I'm going to call the force on the 1 by the 2. I mean, that force on the 1 by the 2 does include the normal force in one direction and the friction force in the other. It just doesn't help us to break it up that way, so we're not going to. Okay. So this is, and this notation, I'm going to bring this up later, but we're going to use this a lot. That's the force on 1 by 2. And one sort of unfortunate thing is there's no standard for which one is the first subscript and which one is the second. So if you want to be really clear to people, you can write out the words on 1 by 2 in the subscripts. It tends to be, I think, that physics people would tend to write the force on 1 by 2 as the force 2 applies to 1, so it would be F2-1. It would be the opposite thing. That really is unnecessarily difficult to get straight. But in engineering, this is a more common way as far as I can tell, so that's how we're going to do it. But you can always write it out in words if you want to be clear, you know. Okay, the free body diagram of the 2 kilogram there's a weight force of 2 times 9.81. There's a friction contact with the ground. So I'll call this the force on the 2 by the ground. Let me move this. I got to fit that 10 in there. There's the 10 Newton force. And then there's a friction contact applied by the 1 kilogram. We can write that as the force on the 2 by the 1. And the nice thing about this subscript notation, whether you're using, you know, the physics convention or the engineering convention, in either case, flipping the subscripts because of Newton's third law just means the negative. Okay, so F21 here is equal to negative force vector of F on 1 by 2. And the point of doing that, it's important to recognize that whenever you can make that switch. Because F21 and F12, those are different variables, right? So if you don't recognize that there's that Newton's third law rule determining the relationship between them, that's 2 more variables you would have to find. Well, you probably don't have 2 more equations to find 2 more variables, you know. So this is often the difference between being able to solve a problem and not being able to solve a problem. You always have this battle going on just constantly between, like, here's how many variables I have. Do I have enough equations to solve for all of them, you know? So let's see if we could solve this. Again, I'm doing this in 2D. So for variables, we have 2 there, 2 there. If we didn't recognize we had to make this switch, that would be 2 more and we'd have 6. But since now we know this is negative F12, we already have those variables. So we have 4 unique variables. How many equations do we have? Newton's second law, x and y components here, x and y components here. So 4 equations, 4 variables, and we can solve this. Okay? Any questions about that? Okay, well, let's do one problem example. So let's say we have an incline of 20 degrees. And we have a 5 kilogram block on the incline. And it's connected by a cable to a 1 kilogram. And this is in static equilibrium. Meaning that the acceleration is 0. And we're assuming that this is a friction contact. Otherwise, most likely, unless I got really lucky with the masses and angles, this would be accelerating one direction or the other. So we want to find the reaction forces. Okay, so let's start with the simpler one. So the free body diagram of the 1 kilogram. There's a weight force down. That's 1 times 9.81, so 9.81 newtons. There's a cable force up, I'll call that T. And now let's write out Newton's second law for static equilibrium. So in a standard coordinate system, we have 0, negative 9.81, plus 0, positive T, is equal to zeros. You can use the y equation. It says negative 9.81 plus T is equal to 0. So T is equal to 9.81. This is one place. So doing statics before dynamics is nice because you can just get really good at dealing with the forces before you start worrying about the stuff on the right side of Newton's laws. One place where it makes you sloppy, so be careful to notice this. The tension in this cable in static equilibrium is just equal to the weight of that hanging thing, right? And you can just eyeball that. It's always going to be true in these problems. But remember that if this thing was accelerating, that would not be true. And so we're going to go through doing this calculation every time so that you don't get in too bad of a habit of just looking at a problem like this and saying that cable tension is the weight of the hanging thing, okay? We're going to keep acting like we don't know what it is, like we're stupid, okay? All right. All right, so now the free body diagram of the block of the on the incline. We have the weight force down of 5 times 9.81, 49.05. We have the cable force. That's the same as this one. So this is T, and we just calculated what T was, so we know that. And then the last thing we have is a friction contact between the incline and the block. So I'm going to write that like this. And since we don't have any other R's, I'm just going to call that R, but you could call that the force on the 5 by the ground or whatever. For this one, you have to use cosine and sine a little bit. Notice that there's only one place, I guess, we have to use it. It's for that cable tension. But notice that what we're doing to find the components of that is stuff that you just did a bunch of times in those vector exercises. You're just figuring out the components of a vector with a magnitude of 9.81 that makes an angle of 20 degrees with the positive x-axis. So the vector components are 9.81 times cosine of 20 degrees, 9.81 times the sine of 20 degrees. And that's 9.22, 3.36. So now if you put this together into Newton's second law, I'm almost done. You have the weight force, 0, negative 49.05. You have the reaction force R, that's 9.22, 3.36. Sorry, that's not the reaction force. That's the cable force that we just calculated. You have the reaction force, and I'm just going to break that up into components, Rx, Ry. Now you've put in all of the three forces in the free body diagram, so you know that's it. Static equilibrium says it's equal to 0. And you can calculate these components, and you get that this R vector is equal to negative 9.22, positive 45.69 newtons. And if you want to visualize that force, it's, it's a little bit in the negative x direction, a lot in the positive y direction, so it's over this way or something like that. Yes?
And that was the normal and the friction force?
Yes, that's the combined normal and friction force, or you can just think of it as the friction contact force. That's always made up of those two. Any other questions? Okay, that's it.